So we have quite a few eminent physicists and scientists on this slide.
Yeah.
So, Bobby, the Hall census is based on something called the Hall effect.
Correct.
And it's one of the best known and earliest exploited solid state sensors, right? So you said, when I asked you why don't we use MR sensors instead of Hall sensors, your first answer was, oh, they've been around for a long time. And you're right? So it's based on something called the Hall effect, which we're going to talk about. It was discovered by a scientist called Edwin Hall here. Okay. And it was a groundbreaking discovery in the 1870s. And he was only 24 years old, right? But then you might be wondering, how come he did not win the Nobel Prize?
What happened?
I think in the 1870s, there wasn't enough follow-up work and any any kind of applications of this discovery for Edwin Hall to win a Nobel Prize. However, fast forward to 1985 and 1998, 4 different physicists won Nobel Prizes for discoveries that associated with the Hall effect. Right, so very, very important kind of principle, and in the Hall census we use this principle. Okay. All right. So what do we see here?
I see some sheets.
Yeah, right. So imagine you have a current conducting strip here.
Okay.
It has.
And you're sending some current through it.
Yes, I'm sending some current through this here. Right here, comes out here.
Okay.
Now this strip has a thickness of D. Okay. Let me do this. That's probably better. And this is the current we are sending through, and it has a width of W. Okay. So when you send a current in this direction, you'll have your electrons here, as you can see, flowing in this direction. Correct?
Yeah.
Now, let's understand.
So the current flows.
Current flows. That's it. That's all.
Then what happened?
That's all Hall census is about. But then, in the last slide, we talked about applying a magnetic field. Right? And what did we say? We applied the magnetic field, let's say, in a perpendicular direction. So this is the planar. Yeah. So this is the planar field, right? And you apply a magnetic field, which is 90 degrees.
Okay. To that plane.
Here. So what Edwin Hall found out was, right? So you send a current, electrons are flowing this way, fine, measure something. When you apply magnetic field, all of a sudden, you could measure a voltage here.
Or if you measure across that.
Now, here you have some voltage, right? Let's see a voltage supply.
To make the current flow.
Right? So it goes here, comes back here. You have some voltage.
Yeah.
So fine. Now if there's no magnetic field, you measure a voltage.
Yeah.
Right? And then if you don't have magnetic field, this voltage will be equal to that voltage, no?
Correct. If magnetic field is not there, then V should be 0.
This V should be 0.
Correct.
Yes. This V should be 0 if there's no magnetic.
Yeah.
But when there's magnetic field,
that's what he has observed.
Yeah. But when you apply a magnetic field perpendicular to this plane, you could measure some voltage here.
How come?
Exactly. That's quite strange, isn't it? I mean, how come when you remove the magnetic field, this goes back to 0?
Yeah.
So, now, we have our current conducting strip.
Okay.
Right? Now, we also have, remember initially our electrons are flowing in this direction. Okay.
Without the magnetic field.
Now, when you apply a magnetic field, right? So, in the presence of a magnetic field, you see that this electron here tends to drift in this direction.
Uh-huh.
Okay.
Why?
To one side of the conductor. Why
There is
that?
some force.
Yes. There must be some force, because otherwise, how would this electron, which is supposed to just travel
Straight.
straight,
It gets deflected.
it gets deflected, right? Now, as you said, you just said in the presence of a magnetic field, what do you say?
Some force.
Yes. Electron gets deflected. And because maybe,
I heard something called Lorentz equation.
oh, maybe there is a force
Yeah.
acting on this particle.
Correct.
And you're correct. When there is a applied magnetic field,
Hmm.
there is something called a magnetic force, as you
Yeah.
can see here, right? That is acting on that electron. And that force is a function of the magnitude charge of the carrier, which is Q. Okay, I'll write that down.
Yeah.
Vd is the drift velocity.
Yeah.
So it kind of drifts to the side
Yeah.
at a velocity Vd. Okay. And then this is your applied magnetic flux density,
Mm-hmm.
right? So what your Q is magnitude of the charge carrier, correct?
Yeah.
Which is this one here. And I think there's a number for this. So this is basically a coulomb, 10 to the minus 19 coulomb, a charge, basic charge. Vd is the drift velocity of the
Electron.
Yeah, let's say.
Or charge carrier.
Yeah, charge carrier. In this case, electron.
Yes.
And that's in meters per second. Okay, that's a velocity. And B is your applied
Magnetic field.
magnetic flux density. And let's say that is
Weber per meter square.
ampere per square Tesla. You like ampere per square. We can also ampere per square.
Yeah, Weber per meter square.
Weber per yeah.
Yes, yes.
Ampere per square is H.
Yes, yes. SI unit.
Meter square. Okay. Now, when this drifts to the side, right? Now, of course, there are many electrons. We're just showing one here, right? Now, there'll be a buildup of charges on one side. So this electron, let's say, is going to my left.
It goes to that side and then finally goes out. Yeah, there will be some accumulation on that.
So there's an accumulation. So what happens when there's an accumulation on this side?
Means there will be some electric field formed due to that.
Yes. So there will be also an opposite charge accumulation on this side.
Correct.
Correct?
Yeah.
And this means this gives rise to an electric field.
Yeah.
Now, I hope our students remember Maxwell's equations, plus to minus.
Yes.
Goes this way.
Yeah.
Correct?
Yeah.
Now, this electric field is voltage divided by the width of the...
Yes. Yes.
Right? So, V is the voltage and W is the width of the conductor. It's in, let's say, meters. This is in volts, obviously. Now, because there's an electric field, that gives rise to another force.
Another force, yeah.
Which is the?
It's the charge into electric field.
Yes. Electric field is the electric force that acts on this test charge.
Yes.
Right? Charge. So in this case, as you said, let's call it Fe.
Yeah.
Okay, this is Fm. Q times E. Now, that's in the same direction as the field.
Which field?
That's in the opposite direction of the electric field.
Why is that?
In this case, we're talking about electron here.
Yeah.
Why is this now in the opposite direction?
Or it gets attracted towards the positive side.
Because if you have a field, if you put a positive charge, it will be pushed away in the same direction as the electric field. Negative charge, it will be the other way around.
Yes.
Right? Yeah. Okay. So far clear.
So that means now finally the current may flow start straight.
Yes. So what happens is, so this is what happens, right? So this is a process.
Yeah.
Right? So normally what happens
finally these two forces will become equal.
Exactly. Very good, Bhavesh.
I thought that's what you're trying.
You might also win the Nobel Prize. So charges are built up until equilibrium is reached, right?
Yeah.
Which means your Fm is equal to Fe, correct?
Yeah.
So this we know Q VdB, okay? This is QE. We know E is volt over width, sorry. Then this voltage that we measure, okay, can be written as VdPW. Okay? Now, what about the current flowing in the plane?
Current flowing in the
in the conductor.
Oh.
Because remember, after some time, there is some current flowing.
Yeah.
Right?
So the current will flow like initially.
Current flow initially, but then how is that related to what we are observing? So, for example, current is what? Current density times area. Okay? We also know J is the conductivity times E. Right? Then the electric field is the drift velocity divided by
W. Mu n.
This is the mobility.
Yes. Yeah.
Of an electron. Okay. And this is your drift velocity.
Got it.
Now, if students are confused, drift velocity divided by mobility, right, is your electric field.
Yeah.
If you use the units for this one and this one, you get volt per meter.
Yeah.
Okay. Straightforward. Now, your sigma, which is your conductivity, right? That's the measure of the ability of a material to conduct an electric current. Okay. So in that case, that is N, which is the density of electrons, right? The amount of electrons you have, times Q, which is your charge carrier. We already know that. And the mobility. Okay. Correct. Now, if you substitute this, to this, okay, then you get. So I think here we need to tell the students this is the density of electrons. Okay, density of electrons. Now, if you substitute all this to this,
okay,
then you will get J is equal to N Q V D. Now your current then is N Q V D, right, times dW. Why dW here? Because that's your cross-sectional area. Okay. Then you can write the voltage now in terms of your current, the magnetic flux density,
and some constant,
and the charge carrier, the number of electrons available, the density, times the thickness.
All that is fixed for a material, that is once you select a material and dimension.
Yes, once you select material, this voltage can be written like this. Now, what does this tell you?
It just says output voltage is proportional to B.
And?
Provided current is fixed.
Or current is fixed. And what else? This material should also be very thin.
For this to have very good sensitivity.
Yes. And you should have
enough number of charge carriers.
Yes.
Number of electrons.
Not too much. Because if this increases, this will also decrease.
Yes.
Right? That's a key point.
Got it. Oh, N is in the denominator.
Yes. And we'll talk about that later.
Mm.
Because now we are talking about a conductor. Okay.
Okay.
Right. But maybe, I mean, when the discovery was made, I'm pretty sure it was made using a conductor. But later on, they found out maybe it's not the best. Got it. Okay. All right. So
if you want to use as a magnetic field sensor,
yes,
we will send a fixed non-current
yes,
and then look at the V.
but V here is transverse
Yeah.
to that
Correct.
current direction, right? That V is not the V that's giving
Yeah.
current.
Look at the V means this is a V that will be proportional to B.
Yes.
Both way.
In fact, let's call this VH or something.
Yeah. Whole voltage.
Whole voltage, right? And this I is from a normal
Some other source.
Some other source, V supply or something. Okay. Okay. Now, there's a very important parameter in the Hall effect called the Hall coefficient.
Okay.
Okay. What is the Hall coefficient?
So it is not that N and other terms that you had there.
Yes, we are getting to that.
Okay.
Yes, you're right. Yes. That coefficient is important.
Yeah.
Right. So that's the ratio of the electric field. Field to the product of what will be B and J.
Yeah.
Okay. So then we can call this RH E divided by JB.
Okay.
Okay. Now we know that's E, right, divided by I over A times B, right, which is then equal to VD divided by IB.
VD is that drift velocity.
VD is the drift velocity, yes. But I think J is in terms of drift velocity, no? J we found in terms of drift velocity.
Correct.
So then if you substitute that there, right?
Yeah.
Then you get this RH in terms of VD and IB. Now, what does that say? V equals RH times IB over D.
Yeah. V here you mean VH.
Yeah, sorry, yes, that's a good point. Yeah, this is VH, right? This is VH.
Yeah.
Right? That should be small actually.
Yeah.
So V then is, remember this is what we found before.
Yeah.
And you said this, right?
Correct.
So then that means what is RH equal to?
1 by Qn.
Exactly, 1 by Qn. Okay. So that whole coefficient is
it's dependent on that material.
Right. So now when you're talking about all these materials, what is that telling you though? Are you thinking the conductor is the best for this?
You already gave a hint, I think, to me. Because it's very conductive, then it's not. So N is in the denominator.
Yes.
So it should be.
But it's not just that. Because RH now is the number of density of electrons and the Q. But remember our electrical conductivity, right? So in fact, you could also write this RH, which is your Hall coefficient, in terms of conductivity and mobility. Okay. So in this case, ideally, to maximize this Hall voltage, your N should be
small. Yeah.
Okay. Your RH should be high.
So if N is small, RH will be high.
High, yes.
Yeah.
It should be high, and D also should be small.
Yeah.
Okay.
Correct.
Now,
Oh, what is this?
Now, let's write these equations down. So I want to discuss this in terms of these equations. Got it? Okay. So let's say VH is equal to 1 over cube N times IB over D. Okay. We can also write this as in terms of the Hall coefficient times IB over D. And we also know the mobility of electrons is related to the Hall coefficient. So, if you're talking about conductors, right? I gave you a hint before. Do you think it's the best material we can use to maximize this Hall effect?
As per the hint, no.
Why? Why do you think?
Because N will be large.
N will be large, right? Because if you look at any conductor, a good conductor,
A lot of free electrons.
A lot of free electrons, right? So,
but then is insulator is the best?
Huh?
Is the insulator best solution?
No.
No.
But
there should be a possibility for current flow.
Yes, but I don't want the students to be confused because conductor has a lot of electrons, right? But why is that bad? Because there are 4 electrons flowing them. But if it's too much, then that deflection, right, will be minimal, right? So that voltage will be very small, right? Imagine if you have a lot of electrons and the Hall voltage depends on this deflection, right? But if you have too many electrons, then that deflection will have a very small effect on this Hall voltage. Okay. However, it's more pronounced in what we call semiconductors. Okay. Why? Because semiconductors have lower carrier density. Now, if you talk about silicon, which is probably the most
widely
used and probably the most popular, no?
Yes.
Silicon. That has, this is a silicon atom here. Has 4 covalent electrons.
Yes.
Now, however, the problem with silicon is, okay, it has a lower charge density than conductor, but you should still have some free electrons, right?
Correct.
But for these electrons to break from the valence, the covalent bond, the thermal energy that's required is generally much higher than room temperature.
Yeah.
Okay. So good, but not great. So what do we do?
You will dope it.
Exactly. Right. So what we normally do is we dope this conductor. Okay. Silicon with, we intentionally introduce some impurity atoms. Now here you have silicon that's doped with boron. Now boron has 3 electrons and 1 hole. So when you add them together, right, you have 1 hole. Okay. So we call this boron is an acceptor because it accepts electrons. Okay. And this is what we call a p-type semiconductor.
Yeah.
Okay. If you look at the diagram here, you have silicon and you're doping it with phosphorus. Now, phosphorus is an extra electron.
Okay.
So that's 4 and 4. Normally,
1 is free then.
1 is free. Okay. And that just roams around. Right. So this is what we call an N-type semiconductor. Okay. So a positive type and now negative type is easy to understand, right? Because an electron is negative. Why is this a positive type?
It's a 1 electron is missing there, so it's a.
But what moves this?
That absence is moving.
No, that's a really good point. The absence is moving.
Yeah.
So I mean, I thought because when I first started studying this, I was a bit confused. It's like, how can a hole move, right?
Yeah.
I think for the students, the easiest way to probably kind of try to understand, have they done semiconductors?
I think they are doing one course soon.
Yeah. The easiest way to explain this is, if you have a tube with marbles, right? Now, in an N-type semiconductor, you add an extra electron. So what happens is your electrons move this way. You add something, this will pop out. Yeah. Now, in the other one, the n-type, we talked about a hole. So in this case, the easiest way to kind of think about this is, in fact, you don't really pop out anything, right? Let's say you have a hole here. Your hole actually moves this way. Your electron moves this way.
Mm-hmm.
So it's this hole that is being moved to the other side. I don't know if that makes sense. But I think the easiest way for the students to think is think of this as a negative carrier and think of this as a positive carrier. Yeah, that's probably the easiest. Yeah. Right? Now, if you look at this picture, do you notice a difference, so Bobby, in this picture? This is the picture we had before, but some things have changed here.
Direction of electric field?
Yes, because before we had a negative charge.
Correct.
Right? Now, imagine if a hole is moving. So you have a positive charge.
Yes.
In this case, your field and your electric field will be in the same direction.
Yeah.
Right? And your magnetic force will be acting on this positive charge. So the positive charge will then move here.
Yes.
Okay? So depending on if it's a hole or a electron that is moving in this semiconductor. Right? So that's another important aspect.
So depending on whether it is n-type or p-type.
N-type or p-type. Yes.
Maybe this is a way to detect also whether it is n-type or p-type.
Actually, you're right. This is also a Hall effect is used to detect if it's n-type or, because see, it is easy, right? If you think about it.
Because the polarity of this voltage will change.
Exactly. This polarity will change. So if the students go back, right, in the first slide, this was here, right? Now, depending on n-type or p-type, as you can, yes, polarity change. Okay. So, doped semiconductors are the best material to be used for Hall effect. This is just a nice animation. I thought I'll show the students. If they're still confused, right? This is all what we've been talking about, right? So you have your current, right, going in this direction.
Yeah.
And then you have a magnetic field, and based on the magnetic field, your electrons or your positive charges are pushed to the side, which creates an electric field. And the voltage that you measure is across this.
Yeah.
Okay.
Yeah.
So in a nutshell, this is what we've been talking about all this time. Okay.
Nice.